How do you do? This is Mr. Klein, and I'm going to be doing a brief lesson today talking about an introduction to limits. Let's jump right into it. Imagine that we have a curve, and it's moving along on this side of 2, and it's moving along on this side of 2, but that at 2, suddenly there's a point discontinuity, like so. There are two different concepts that we're going to be studying over the next few classes. One of them is value, and the other is limit. Now, at this point, and at this point, and at this point, and at this point, and 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 every other point on the curve except for at 2, the value and the limit are identical to each other. We tend to be interested in points like 2 where they are not. So let's begin by talking about the value at x equals 2. The value at x equals 2 is what you get when you plug 2 into the function. And if you plug 2 into the function here, the point that pops out is 40. So the value would be 40. F of 2 equals 40. The limit is different. The limit doesn't care what happens when you plug 2 into the function. The limit is interested in what's happening from the left side and what is happening from the right side. And we can see that both from the left and the right side, we are getting very, very close to 20. So we say the limit as x approaches 2 of f of x is equal to 20. So we've got the value at x equals 2, and we've got the limit at x equals 2. And again, they are not the same. What's up, dude?
Can we watch another one?
Sure, knock yourself out.
Oh, God.
So let's give a formal definition. We say that L is equal to the limit of a function as x approaches c, c being some constant value, if, if and only if, you can make f of x as close to L as you want by moving x close to C, but not equal to C. In the case of the example that I've given you right here, 20 is our limit. You can see that we can get as close to 20 here on the y-axis as we want by moving the x value closer and closer and closer to 2. As this approaches this way, this approaches this way. Same on the other side. What's important is that we note that we don't actually care about what happens at C. Okay. On a practical level, if you're trying to find the limit of a function, let's look at this function right here. If you can just plug in the limiting value and get a number, you're done. So for instance, if you look at the limit as x approaches 0 of this function, you plug that in, you would end up getting which is going to leave you with 1. And if you plug in 1, just trust me on this, you're going to end up getting 2. And if you plug in 2, you're going to end up getting 3. So in each of these cases, the limit is easy to find because it is just the same as the value. However, look what happens when we plug 3 in. The numerator is equal to 0, and the denominator is also equal to 0, which means, uh-oh, we have an indeterminate form. An indeterminate form tells us that, let's plot this point, this point, this point. If we were to look at the function, it's going to be undefined at 3 because 0 can't be divided by 0. But it also tells us that we can't determine the limit just based on this information. There might be a limit and there might not. As I am looking at the removable discontinuity right here, I'm thinking it seems like as we approach 3 over here, we're getting pretty close to 4. Okay. So, now, same equation right here. When you're determining limits algebraically, 1, if you plug in x equals c and get a number, you're done. That's good. If you get 0 over 0, then you do some algebra. And plug in again. In this case here, we might take the numerator and rewrite that as x minus 3, x plus 1. And when that happens, we notice that we have an x minus 3 here and here, and they cancel. So this limit is going to be the same as the limit of x plus 1. Now we plug in the 3 again. We get 3 plus 1 is equal to 4. Two things I really want to emphasize with you right here. First is that 4 is the same number that we guessed it was based on the graph. Second, if you look at this graph, see how it's a line? This line is y equals slope of up 1 over 1x plus y-intercept of 1. So y equals x plus 1. And when we simplified this algebraic fraction, we ended up with x plus 1. That's not on accident. Okay. One more example. Let's suppose we run into something like this, where we have a cubic divided by a linear. Once again, the first thing you're going to do is plug the negative 5 in. And in this case, you're going to once again get 0 over 0, which means that we need to factor the numerator. We know that when we factor the numerator, we're going to get x plus 5 as one of our factors. As soon as you see 0 over 0, you know that this is a factor of both top and bottom. It's not so clear what our other factor is going to be, and so this is where you might choose to synthetically divide. So when we synthetically divide this by x plus 5, we plug the root of the denominator in here. We take the coefficients of the numerator and we list them. And then the process goes like this. Drop the 1, multiply to get negative 5. Add them together, multiply. Add them together, multiply. You should get a 0 right here. If you don't get a 0 in this position, go back and check your work. You made a mistake. So we've got a 1 and a 1 and a negative 2. That tells us that our factor here will be 1x squared plus 1x minus 2. These cancel. We end up with the limit as x approaches -5 of x squared plus x minus 2, which ends up being equal to 18.